feel like that's a trick question.
Which part? Whether the homework was easy?
Whether or not it was. I mean, because if you say it's easy, you're just gonna make it like 10 times harder.
I was going to do that. I was going to do that anyways.
True. Okay.
All right.
If you say it's hard, you're still gonna make it 10 times harder. So.
Well, it all depends. If I can't solve it in class, I usually don't give you the assignment, right? Yeah. So don't you hate that when teachers like, you know, they give you something to do as a homework assignment and you're like pretty sure they can't do it. Like I always hated that. like there's just no, I mean, how are they even going to grade it? There's just no way they could do it.
I feel like I had a high school like technology teacher who did that once or twice.
Yeah.
Like he tried to teach us like HTML stuff and doesn't even know how to do it.
Well, maybe that makes more sense because at the high school level, sometimes you have teachers that, well, first of all, high school teachers have to get trained to be teachers. So actually becoming a high school teacher is easier, or sorry, more difficult than becoming like a college prof, other than just the degree, because we never had training to teach. But what you do have, especially in this transition period, I think is becoming more and more common maybe to have computer classes in high school, but you have like, you know, they just pick from the high school faculty who has the best shot at teaching this technology class or something like that. So, you know, you got like the, you know, the football coach comes in and says, yeah, my kid's an engineer. So, and now he's the computer teacher.
My high school actually had a teacher that I think had some sort of technology degree.
Okay.
That taught that. There was another guy who was a business teacher who taught something else. Who taught a like web design class.
I see.
So the technology teacher taught like the Lego Mindstorm stuff and other things like that. The CAD stuff.
Mm-hmm.
And like he knew what he was doing, so but the other guy who just, since he was a business teacher, he sort of didn't really know much about technology stuff.
Is what it is. All right, so last time we were looking at linked lists to give us an arbitrary size collection. And I think right now we're looking at a linked list of integers, right? And so last time we did a AddEnd and RemoveAtIndex, right? So the homework for today was to add AddFront and RemoveFront. So AddFront adds a value to the very beginning of the list. RemoveFront removes a value from the beginning of the list and returns its payload like we did for RemoveAtIndex. All right, so let's go implement this and then we'll go to something more complex that kind of feels like performing surgery, kind of. When you imagine putting something in the middle of the list where you have to unhook pointers and reconnect stuff and don't lose the patient, right? We don't want it to float out into oblivion somewhere in memory. So we'll go into our code over here. All right, this is 300. All right, so here's our linked list, HPP, linked list. All right, so we're going to go ahead and do an add front and remove front. So I'll just steal these two lines here. Add front, remove front. I'll copy those guys because we're going to go now add it to our implementation. All right. Give ourselves our little stubs here to work with. All right, so let's look at removing front first. Okay, so if we're removing something from the front of the list, that means we're going to go to the head of the list, right? That's the dude we're going to remove, but we need the head to now point to the next guy in the list. Make sense? So we can't just immediately remove it. So we're going to kind of follow this policy for everything. Whenever we take something off the list, we're going to fully disconnect it whether we would have had to or not. All right, so I'm going to go ahead and we're going to create a node pointer called this guy CurFront, and this guy is going to be equal to, and actually we can wrap this whole thing inside of an if statement if we want to do some error checking. So we'll say if this dot head, if that guy is a thing, which effectively says that this is not the empty list. We could have also said if the this count is greater than 0, if there's something in the list to return, we're going to go ahead and return it. All right, makes some sense. So if there is a head of the list, we'll go ahead and set the CurFront to the head. Then we'll say this head set next node to this head get next node. So we'll make head, actually we're not setting head's next node, I'm sorry. We're setting head equal to. So we'll preserve the current front of the list, preserve what head points to. Then we'll set head equal to, we'll change the value of head to be whatever head's current next node is. Finally, we'll go ahead and say CurFront set next node to null. This is that part I just mentioned a few minutes ago where we want to have a policy of fully disconnecting it. That way you don't have extraneous pointers to places in memory. Now the reality is since this guy is a local variable of RemoveFront, he will die. He'll go away when RemoveFront is done. So realistically, we can say this line right here is a waste of time, but good practice. All right. The idea is we are physically removing this thing from the list, which means we want to disconnect all of his little connection points. Okay. But we happen to know that this variable will disappear when this is done. But what won't happen is this guy in memory won't disappear. Okay. We don't have automatic garbage collection in C++. All right. So whenever you make a mess, clean it up. You don't want something to point to something else, make it not point to that something else. Don't rely on automatic processes that may or may not happen in the background. All right, so as long as we have something in the list, get the first element of the list, update the head of the list, make the old first element of the list not point anywhere, and ultimately return CurFront get payload, the value that lived there. All right, that makes some sense. So that should be our remove front. Now we want to add to the front. So adding to the front, well, we can say if this head, if that guy's a thing, add it to the front. Else, we could do a couple different things here. We could say we're going to just make head point to this guy, create a new node, but we actually already did that in AddEnd. All right, so the reality is that if this is the empty list, isn't AddFront the same thing as AddEnd? If I have nothing in the list, those guys are the same thing, right? So I'll actually go ahead and just call this AddEnd, passing it, what did I call it, value. So this is, we have an empty list. So AddFront and AddEnd mean the same thing. So I'll just go ahead and call AddEnd because we already wrote that. Make sense? Now, one thing we did forget to do here in remove front. What did we forget to do down here? If I'm in here, does a node definitely get removed? Node gets removed, right? What happens if a node gets removed? Count of our list should go down by 1, right? So one thing we forgot to do down here is we forgot to say before our return statement, this count minus minus. We have taken something off our list, therefore our list is now 1 smaller than it used to be. Let me make sure we did that remove end. Yeah, we did. Okay. Now, if we want to be really good, let me go back to remove front a little bit more here. After I set that next node to null, if we want to be a really good steward of memory, we would go ahead and say delete cur front. And that would actually give back that memory. Keeping in mind that this will work without this line and without this line. These 2 lines aren't required to get this to function. They're required to not leave a mess in your wake. All right, abandoning things in memory and stuff like that. Modern day operating systems probably go through and clean up memory for you, or your programs live in some sort of little pod of memory space when they run. Therefore, when it's done running, it goes through and cleans it up. So this is probably not mission critical, but then you're relying on somebody to come up and clean all your messes behind you. So the real life example of this would be when I make a mess in the kitchen and then I don't clean it up because I just assume my wife will clean it up when she finds it. That always goes over great. I've gotten the quotes that this isn't a restaurant or something along those lines. So if you make the mess, clean up the mess. It's good real life practice and also good programming practice. All right, so back to AddFront. So if we have at least 1 element in the list, we'll go ahead and code AddFront. Otherwise, if it's the empty list, AddFront is the same thing as AddEnd. So we'll just go ahead and call upon our other ability rather than write some duplicate code. Now, yeah, that's fine. So now for AddFront, if we are not dealing with the empty list, what we need to do is we need to create a new node. So we'll say node pointer n is equal to new node, passing it this value. So we're going to create this brand new node that we intend to add to our list. We're going to now make this node point to the same thing that head points to. So n set next node to head. So now our brand new node n points to the same place in memory as head points to. And now what we can do is we can adjust head to now point to our new node. This head is equal to n. So now head points to n points to where head used to point to, and then the rest of the list is whatever it used to be. We don't have to change that at all. All right, make some sense? And then, of course, we did just add something to our list. So we need to say this count plus plus, like that. Why didn't I do this? Why didn't I just say, well, AddFront's going to add something to our list one way or another, so I'll just always increment count? Why would that be a problem in this current implementation? Go ahead. Yeah, AddEnd already increments the count. So if I do it here regardless, I'm going to get a little overzealous. I would have doubled my count for the empty list, right? But I'm not relying on another tool inside of the if. So if I have at least a one list, I'm in charge of adding something to the front of the list. I'm also then in charge of notifying this particular instance of linked list that his count just increased by 1. All right, so that should be AddFront and AddEnd. And we should be able to go now and test this. What is it in driver? So we'll do LL, AddFront and RemoveFront is what we just wrote. So we'll add a couple of things to the front. Let's add a 13 to the front. And then a 17 in front of that. Then we'll display it. So let's just make sure AddFront is working. So when we're all said and done, it should be 17 followed by 13 followed by 4682. Oh, I already wrote that compile. So there's our compile, a.out, 17, 13, 4682. All right, so AddFront seems to be working. It would probably be worthwhile testing AddFront on the empty list just to make sure you covered your bases here. So the first time we call AddFront, we get a 13 added to it. Then I call it again, and now we're adding to the front of the non-empty list. So I should get a 17 followed by a 13 here. But now we're also testing against the adding on the empty list. So there's our 17, 13. All right, now we want to remove from the front. So we'll go ahead and say LL remove front. And we'll go ahead and capture that in the value. And display it. So now we're at, the list will be 17, 13, then we're removing front, so the list should just be 13, and then we'll print out that we removed the 17. Ruh-roh. I'm guessing I did not return a value from my remove front. Oh. Tell me why this is broken. So first of all, this is a good debugging thing. This is the value I got for my value that was returned. Not what I was looking for, right? I was looking for a 17. So let's look at our code here. Why am I returning? What's wrong with this? Why am I getting the wrong value returned? Go ahead.
I was going to say return the memory address, but that's
I'll give you a hint. This line is correct. That line will return the correct value if the correct value is there. Hint, hint.
Above that, you're deleting cur front.
Right here. I'm killing it off. I'm saying, look, not my memory anymore. OS, have it back. Remember I said earlier that, you know, because this is a local variable, it'll be cleaned up automatically and I'm disconnecting everything. But I said, oh, you know, if we make a mess, we can clean it up. Don't clean the mess up before you need to use it. All right, so realistically, what we would probably do is we would say like int value to return is equal to this guy. Now I have the value. Then I can delete the memory and then I can return the value to return. So I'm still cleaning up my mess, but don't clean it up until you've gone ahead and extracted the integer that you wanted from it. Then decrement your count, then value to return. And you really could have put your decrement count anywhere inside of here. Since you're only in this if statement, if you're definitely removing a value. So it didn't matter where you put it. Well, definitely put it before the return statement ultimately, because return makes a function immediately end. All right, so go run this again. We should now get our 17 out of this dude. There's our 17. Very interesting problem. Now, the reason why I obviously did that on purpose, it's good that it happened. Notice the behavioral difference between Java and C++. C++ let me do that. It let me call curfront get payload on a null value. Did it not? Java would have screamed forever. Null pointer exception. What are you telling me to do? You're telling me to call some function on nothing? C++ just says, whatever. And this has to do with the way object-oriented languages are built. We'll talk about that in the 470 class when we write languages. That's offered in the fall, right? So probably several of you should be taking CSC 470 in the fall. So we write a programming language in there. And one of the ways that object-oriented languages are put together is with this idea called message passing. So the idea is that the message we're sending here is called get payload. Who are we sending it to? We're sending it to this dude right here. All right. So in Java, if we yell a message at nothingness, Java screams at you and says, you know what? You're talking to the wall. There's nobody there. Null pointer exception. In C++, say, hey, you want to yell across you want to yell into the other room? You know, bring me a soda. Nobody's in the other room. You're not going to get your soda. But you can scream all you want. Okay, so C++'s behavior is different. There is no exception system in the original C++. There's sort of kind of one since standard template library, but you have to choose to use it. So this is an interesting problem because we did get a result, not an error. And you see this crazy looking negative value and you're like, why is it that? Now, if I was on a different system, might the answer I got there be different than a crazy negative value? Sure, I'm at the mercy of how the implementation of that operating system does when a message is sent to nothingness. Who knows what it's even doing here? Is it just giving me something from like dev null or dev random, just some random output value? Who knows? All we know is they said, I'm not going to scream instead, because the reason they didn't scream is because C++ is designed for performance. They figured, hey, you're the programmer, just don't put errors in your code, right? Easier said than done. So that's one less question that had to be asked. C++ behind the scenes didn't say, if this is a valid memory address, then send the message. Instead, it just said, I'm going to send the message. If it worked out, it worked out. If it doesn't, you're lost. All right, that makes some sense? Okay, important thing that I obviously did on purpose.
I have a question.
Go ahead.
So, after you deleted cur front, it still like held onto the memory address. Is that correct?
Well, cur front still equals that memory address. Yes, if that's what you're asking.
Okay, yes.
But it's that memory address that has been given back to the operating system.
Okay, okay,
So,
perfect.
so if I were to use cur front after this line, I'm using memory that doesn't belong to me. And I'm also using memory that may have been cleaned up by the operating system. We don't know what delete ultimately does. What does it mean? Because at this point, we're talking to the operating system. So we're yelling at the operating system's memory manager and saying, hey, I am done with this location in memory. You can have it back. Now it's no longer our job to deal with that memory. So the operating system is going to do whatever they do. Maybe they load this random negative number in there to overwrite the value that's in there. Maybe they leave the old value in there. We don't know. The operating system writer got to make that decision, which means we shouldn't rely on it because that program might run on different systems. And if we rely on, this is kind of in the same idea as relying on default values. Don't rely on default values. If you want it to hold a 0, put a 0 in there. All right, that makes sense? So this guy is communication with the OS saying, I am done with this memory location, clean it up. But I still, until this function ends, I still have a local variable called cur front that equals a number. And that number is a memory address. It just happens to point to a place in memory that no longer belongs to us. Okay. So I think we tested everything thoroughly now. I think so. So questions about this? This should be the homework. Go ahead. Let's see. So I am removing front here with the 17. You want me to remove it a second time?
Yeah. Or just run the
Okay. I mean, that was the run of it. So this is the list after we removed it. That's displaying the list. This is the value we removed at 17. This is, so the 13 was the display of the entire list. This is me displaying the value that I removed. If I want to remove it a second time and then output it a second time, I'll end up with the empty list. So here I can even tell it to display again. And then I'll show that I removed that 13 as well. So here's the list after I removed the original front. This is what I removed. Then I removed another thing. Here's the list now. It's the empty list. And here's that last thing I removed. Make sense? Okay. So I think these guys seemingly work okay. You know, in your homework, if you didn't do that memory delete stuff and things like that, that's okay. That's something I'm trying to drive home. Here, it's just like in real life, you make a mess, clean it up, even though you will find that with most modern implementations, you can get away without doing that. But believe me, you are introducing potential memory leaks into your program. So don't do it. You make the mess, clean it up. Unless you're in Java, why wouldn't we clean up our own mess in Java? Well, I'm telling you that inside of modern day implementations of C++, we maybe have garbage collection. So even though we might have garbage collection, even if we knew we had garbage collection in C++, we still probably want to clean up our own mess. Why don't we clean up our own mess in Java? Doesn't that seem like something we should do? Is when we ask for memory, we use the new keyword, we should give it back, even if it's going to take it back by force.
We actually like our own memory.
Yeah, that's the problem. Java doesn't give us access to it. Yeah, we're allowed to make our own messes, and they won't allow us to clean it up. Yep.
Like Java?
It is the same thing as C#, but no, because C# does have the ability to give memory back because it also has the ability to work with pointers if you are in it, if you're in an unsafe code block. So I guess I wouldn't necessarily make the connection between C# must have the same thing as Java because they're related to each other. You could start with that concept.
I mean, I don't know if it's like wrong at all, but like I kind of think that like C# is very kind of like Java, but with some functionality that you don't have in Java. Kind of. Like you can work with pointers, for example.
I mean, yeah, you could make that argument. I think that's reasonable, but I wouldn't pigeonhole it so much. C#'s its own thing, and it was, you know, it was a response to Java. Therefore, it has many things that it liked about the Java language in it, but it also took some liberties of doing some other stuff. So I wouldn't be too close to, you know, too quick to label it as something. It is what it is. It's a programming language like any other. Yeah. Oh. All right, so let me go ahead and push this code up. All right, so that is up on GitHub now. Now let's look at what if we are going to add or remove from the middle. Now, one thing you'll probably find, hopefully you did this when you were working on your homework assignment, that with LinkedList specifically, but really this goes for any sort of programming project you're working on, it's going to help to draw pictures, right? To make sure all your pointers hook up to the right things. But we're going to definitely do it for adding and removing from the middle, because a little bit ago, I kind of mentioned it's sort of like surgery, right? We're either removing something from the middle of this list or adding something into the middle of this list. And there's pointers all over the place. And we need to be able to kind of hook them up to the right place so we don't have something that floats out into outer space on us. All right. So let's. So I'm going to give myself a sample list here. Actually, let's make this look extra cool. All right, we'll say that this is the index, this is the memory address, and this is the value that lives there. And I'll go ahead and give myself a pointer off that guy initially as well, because this guy also has a next pointer, right? So this is effectively a visual representation of a node, okay? Payload. This is our envision of, this is the bucket 0 of our list, and this is maybe where in memory it lives. And then it has a pointer to the next place in memory. So I'll make another node somewhere out here in memory. We'll say this is at memory address 124. So this guy points at this guy, and we'll say that this is bucket 1. And let's just say there's a 7 there. And then we'll take another guy. We'll maybe put him down here. And this will be a 13 and memory address 204. And this is bucket 3. This guy point down here. Give ourselves another one. This is a 2 at memory address 451. This is bucket 4. All right, so there's kind of a, oh, go ahead.
So when the node points to another node, it points to that node memory.
Correct.
Okay.
Yep. So this guy has a variable in it called next node.
Yeah.
that holds a memory address. The memory address it holds is where this dude lives in memory, so it would actually hold 451 in this case.
I have a question.
Good.
Did you skip index 2 for a reason and I missed it, or no?
No, I did it on purpose. It was specifically to see if you were paying attention.
Okay, cool.
All those days are one of those days. Yeah, we're just ahead. Well, maybe. All right, so this is our linked list. So I'll go ahead and create my, here's my variable. So somewhere out here we have a variable maybe named LL, and LL points to well, actually LL is our linked list, and LL has a couple of variables, right? We have head, and we have count. And head points to the first element in our list, and count is equal to the current number of elements in our list. So for right now, this would be a 4. All right, so there's a visual representation of a linked list that has 4 nodes in it. Keep in mind that this 0, 1, 2, 3, this is our human way of indexing this. Okay, we're not storing those indexes inside of our nodes. We just happen to say, you know what, in programming, whenever I deal with collections, whether it's a list, whether it's an array, whatever it is, if I'm looking at a string, the first element is typically bucket 0. The last element is its length minus 1. So we're going to go ahead and imagine that our linked list is organized in a similar way. The front of the list is bucket 0. The last element of the list is its count minus 1. Everything in between has its own relative index. Okay, so now we've already written remove front and add front. We've already written remove end and add end. Are we keeping track of tail in our list right now? So I'll give ourselves one more pointer. Tail points to the last guy in the list. That points to the end of the list. Probably be helpful to have it on the other side, but technically tail is part of LL, so we'll just go with this. All right. What if I want to remove, there's actually a special case here. Let's say I want to remove bucket 2. Let's start with that. Okay, so I want to ultimately get this guy removed from our list, which means that I need to extract him. So maybe I say temp and have temp point to this guy. So I have access to him. This is the guy we're going to remove. All right. So we could say node to remove is maybe what he's called. So I somehow get a pointer that points to him so I don't lose him. Now, I want to, in the end, have this guy connect up to this guy. And then I want to have this guy disconnect. Right? That's what I ultimately want to have happen. Let's think about that first move. How do I make this guy point to this guy's next guy? Go ahead. Okay, so the next node of node to remove is this guy. So now we know our destination. How do we get this guy? Okay, so the issue here is I've traversed my list now, and I've gotten to the guy I want to remove. And I know about that guy's next guy, but I don't necessarily know about the node to remove's previous guy, who's going to be the new index. I need to somehow get to this guy. So you mentioned we could start at the front of the list, right? So I could start walking the list until I get to that guy. How do I know I'm at the guy before this guy? What question can I ask that says I'm at the guy before the guy that I'm actually removing? Yep. So I want to keep walking this list. Create another variable here. So this is prevdude. Okay, so prevdude starts off at the head of the list, and we're going to say, is this guy's next guy equal to node to remove? Nope. Set him equal to his own next node. Is this guy's next node equal to node to remove? It is. Previous dude, this guy, his next node is this guy, which is the same node as node to remove. So now I know that prevdude is pointing at the dude that is previous to the dude I want to remove. All right. You believe me with surgery stuff now, right? It's like, well, I thought he was just making it up. So now I have 2 pointers. I have the guy before him, and I have the guy that I'm going to remove. Now I can say, prevdude, set your next node to node to remove's next node. Then I can say, node to remove, set your next node equal to null. And now I've finished, right? I've inserted that guy in the middle. Now, what if I was dealing with, oh, go ahead. Yeah, I have to update my count. So count is now going to be a 3 because I did remove something from the list. Good. All right, and then technically our indexes would change, but we're not storing the indexes. That's just for our human thing. So this would now become our bucket 2. All right, so let's backtrack here. All right, now what if, let's consider some special cases. What if the node I wanted to remove was bucket 1? So I'll start at bucket 0, jump to bucket 1. So I'll have a for loop that'll just go 1 time, right? So now I point to the guy I want to remove. Then I will set prevdude equal to the head of the list, and we're going to keep setting him to his next node until we're at the node that comes before the node we want to remove. Is prevdude's next node equal to node to remove? It is. We're already home. We're already where we need to be. So now we can do that whole disconnect thing, right? Okay. What if? So let's write that case first, since that's kind of fresh in our mind. Let's see, where am I going with this? Here. So we're going to go ahead and we're going to say int RemoveAtIndex, int index. Put that in the header file. Then we'll go to our linked list file. We'll go ahead and write this. All right, now we're only going to do anything if I have a list that has something in it, right? So if this head, if that guy's a thing, then we'll go ahead and potentially remove something. I could do some more error checking, right? I can say if, right here, we'll be a little bit more verbose with our error checking on this one. So I can say cout nothing to remove from the empty list. So I could do something like that. Similarly, if I'm inside this if, I want to ask the question if index is less than 0 or index is greater than or equal to this count. This is Java's array index out of bounds exception. You're trying to remove something from a position that doesn't exist. Make sense? So if I'm asking you to remove bucket -3, it's a no-go. If I'm asking you to remove bucket 17 from something that has 3 elements in it, that's a no-go. Else, I actually have something to remove. What if my index is equal to 0? Good. Call remove front. So if index is equivalent to 0, I'll go ahead and just return this remove front. Already wrote that logic. Why write it again? And remove front will do the count minus minus thing, right? Else if, what would be the index of the last legal position in our list? If index is equal to what? Good. Yep, so this count -1. So if I'm looking at an index that is the last thing in the list, then what do I do? Return this remove end. Else. We are removing from somewhere in the middle. This is where the algorithm we just discovered comes from. So go back here. We're going to need a couple of variables here, right? We're going to need a node pointer called prevdude. We're going to need a node pointer called node to remove. So node pointer prevdude, node pointer do to remove. All right, and we're going to start do to remove off at being equal to head. All right, so first thing we need to do, go back here. And actually, we can start prevdude off at being equal to head as well. All right, but we're going to do this in separate steps. So the first thing we need to do, if we're either removing index 1 or index 2, something in the middle, is I need to get node 2 to point to the node that we're going to return. So if I'm going to make it go to bucket 1, I'm going to set this guy equal to his next node 1 time. If I want it to be bucket 2, I'm going to set this guy equal to his next node 2 times. So I'm repeating something. I'm going to have a for loop that's going to go through index number of times. So we'll say run do to remove to the correct index. For int I is equal to 0, I is less than index, I plus plus. Do to remove is equal to what? We're trying to accomplish this. I called it dude. Here, we'll just update it here because I like that name, dude. Dude to remove. So how do I make dude to remove traverse through the list? How did I get him to go from here to here? I said do to remove equal to what? Solving one little problem right now. How do I make this variable, instead of pointing here, point to here? It's the only problem we're trying to solve right now. Go ahead. Who's next node? So this guy, I could do it through PrevDude. Right now, it'll work through PrevDude. But if we pretend like PrevDude's not in the, this wouldn't work consistently. This guy is going to get set to his own next node. Because this node's next node is equal to this guy. So right now, do to remove get next node is this. And I can set do to remove equal to his own next node. Do to remove is equal to do to remove get next node. That'll walk them to the next spot in the list. And I do that however many times I need to get to the right index. If I'm getting to index 1, I do that once. If I'm going to index 2, I do it twice. Index 3, I do it 3 times, so on and so forth. Okay, so when this is all said and done, do to remove should point at the value we're going to remove. Now we need to make PrevDude get to the place where it is pointing at the node right before the dude we're going to remove. Now make PrevDude point to the node right before dude to remove. And we really could do this 2 separate ways. But let's start with the way that we described before. We want to keep walking through our list until we get to a node whose next node is due to remove. So while PrevDude get next node is not equal to due to remove. Well, that's not a true statement. So while PrevDude's next node is not the node we want to remove, we want to set PrevDude equal to his own next node. Make him move down the list. PrevDude is equal to PrevDude get next node. We'll set him equal to his own next node. This will walk him down the list. We're going to keep doing that over and over and over again until PrevDude is finally pointing at something whose next node is due to remove. So now, since we're here, what is another way we could have written the while loop above? Go ahead. Yep. So you could just use the same for loop as we had before and only go to index -1 and then do this inside there. The first one we ran up to index, the second one we ran up to index -1. That's the dude right before the dude we want to remove. Okay. I happen to like the while loop, even though they both give us the identical answer. Okay. Well, I think that I like the way that looked. All right. Does that make sense? You can choose which of those algorithms you like better, but any way you cut it, prev dude needs to point to the dude right before dude to remove. Now, everything is positioned and we are ready to operate. So now we go back to our picture and we say, what do we do next? Dude to remove is pointing at the right place. Prev dude is pointing at the right place. So the first thing we're going to do is we're going to set prev dude next node equal to dude to removes next node. So prev dude dot set next node is equal to dude to remove dot get next node. Prev dude set next node is equal to dude to remove get next node. So that does this step right here. Prev node set next node equal to dude to remove get next node. Make sense? Then, what's the next thing we do? We set dude to remove next node to null. Dude to remove set next node to null. Now we have the thing we're going to remove. We actually want to return the payload, the 13. So we're going to go ahead and preserve that. That way we can delete this memory. Int value to return is equal to dude to remove get payload. Then we can say delete dude to remove. Then we could say this count minus minus because we have removed something. And finally, we will return value to return. All right, so we were a little bit verbose here. So we said prev dude. Now, well, we'll look at this, how we can make this a little bit more efficient here in a second. So we could say prev dude and dude to remove both start off at head. This positions dude to remove at bucket index. This positions prev dude at bucket index -1. Down here, then we do our actual logic. We set prev dude's next node equal to dude to remove dot get next node. Then we update dude to remove's next node to be nothing. That fully disconnects them from our list. Then we extract the value that we're ultimately going to return, the integer. Then we delete the memory address that we're removing. We decrement our count and we return our integer. So next question is, how can we write those two loops as a single loop? How can we accomplish getting node or dude to remove and prev dude set to the correct places inside of a single loop? And I'm not even necessarily arguing you should do this. This kind of says something we talked about last class, where get it working first, or maybe 2 classes ago, and you probably heard me say it a bunch of times. Whatever way makes the most sense to you, do it that way first. Then if you think it makes sense to clean it up, go ahead. But from an academic perspective, this is an interesting question. How can I accomplish both tasks inside of a single loop? How can I get dude to remove and prev-dude to be positioned in the correct places using only one loop? Take about 2 minutes and think about that. And then I'll ask for answers, preferably from somebody who hasn't answered recently. But I'll take whatever I can get. So the question you're answering is this: how do I get prev-dude and dude to remove set in a single loop? That is, accomplish what both of those loops, those two loops, accomplish. All right, what do you got for me? Maybe somebody online? See if they're still at their seats. Was this the class that had the movie playing in class online? Maybe that was just yesterday. I think it was in the 250 class. Somebody unmuted their mic. I don't know. There's a movie playing in the background that had some entertaining language.
You want them to give them the benefit of the doubt too when they're.
Yeah, I don't really want to. All right.
Yeah, I get that too. Yeah. If you're looking at a positive light, it was a rumor.
Well, I mean, it's not that big a deal that it had questionable language, other than the fact that it's on the recording. But it was more that they were watching a movie during class, or in the same room where a movie was being watched during class, instead of focusing on their academic success.
I mean, it's possible they have a roommate that refuses to order.
All right, go ahead. What do you got for me? We're only allowed one loop. You want to put the while loop inside the for loop, so you do this multiple times?
Somebody put it in the chat in Zoom.
Oh, isn't that supposed to be Emily's job to tell me when something's in chat?
Now Jason's job.
You people. Okay, so the thing was, couldn't you just put them both in the for loop and then embed an if statement asking if prev_dude is due to remove? You probably could pull that off, putting them both in this for loop. And then ask a question in here. But what I might suggest is we have the for loop only go to index -1. Do the prev_dude thing and the dude to remove thing inside there. And then in the end, just do one more pass where dude to remove is equal to his own next dude. So this code right here will accomplish getting both of those pointers to the correct places. This loop runs them both to where prev_dude should be. One more logic statement here says, now make dude to remove point to the place he needs to point to. That make sense? So my feeling, this is the better way of writing it long term. Now, if you don't like controlling two variables at once within a single for loop, it's not the end of the world. Is there really anything wrong with setting dude to remove and then setting prev_dude? Are our computers fast enough today that this is probably rarely going to be a problem? And doesn't this allow us to walk through our algorithm that we drew pictures for over here, step by step by step, accomplishing each little micro task? Because that's where we run into trouble, right? Those of you who found this last homework assignment difficult, you tried to solve the entire problem at once, rather than solving one little step of it, and solving the next little step of it, then the next little step of it. A little bit ago, I asked the question, how do we make prev_dude? How do we get this job, this one job? How do I make this guy go from here to there? That's the one tiny problem we were solving. Make sense? And you'll find out that all hard programs are made up of a bunch of easy parts. And if you just solve the little tiny problems one at a time, you eventually will get to a working solution. So don't necessarily try to think about the problem in too much complexity. That's where drawing the picture helps. All right. So I would be inclined to say, leave the code looking like this. This sets dude to remove to his position. This sets prev_dude to his position. Now, if you had done those out of order, then you could have just set prev_dude and then set the thing, and you would have actually stumbled upon the right thing. But in any case, we're solving two separate tasks here. We're solving them independently, even though they could be solved dependently. But who cares? Not a big deal. All right, so question about remove an index. So now we can go back into our driver here, and I'll go ahead and add a bunch of stuff in here again. And let's just say add@index, and the index we're going to remove from is, well, we'll just say 2. So it should be 17, 13, 2864. So we'd be removing the 2 from it, right? Let's do 3. I'll remove the 8. Oh, did I have it? Oh, this was the original list, 4682. I removed bucket 3, which was the 6, and then here's the new one with the 8 removed. It worked, I just said it wrong when I said it out loud. So my original list looked like this. This is bucket 0, bucket 1, bucket 2, bucket 3, which is the guy I said I'm going to return. I then removed that 6. That's the guy I removed. And now I have the 4 that points to the 8, which points to the 2. All right, make some sense? All right, so I'll go ahead and push this. Oh, Ninja, what is happening? Well, I'm going to eventually push this. My keyboard, does it type over here? Yeah, it types over there. I'll just close this and open a new terminal. All right, so then homework. Write add at index, which is similar to the remove at index that we wrote in class, but this method allows us to add a value at a 0 based index in our linked list. Submit the GitHub link and the selfie val. Questions, comments, concerns, bribes?
I have a question.
Sure.
I think inside of RemoveAtIndex, I don't think you decremented the count, but I don't remember. I'm just curious if you did and I just missed it or not.
Let's take a look. Yep, I did.
All right, never mind, I just missed it. Thank you.
Any other questions? All right, I will see everybody on, what's today? Tuesday? I'll see everybody on Thursday.